Okay, let's dive in. We've got some really interesting material here, looking at two, well, pretty different paths for farming's future. Think high-tech factories versus low-tech forests.
Exactly. And it's all spurred by this challenge at the Skovsgaard estate, which Kesser and Steen looked into.
Right, the core question being, how do you manage a large farm shifting towards rewilding, keeping cattle, managing waste, but also needing surplus income and, crucially, renewable energy?
That's the puzzle. Could an old place like Skovsgaard actually become a blueprint for this? You know, carbon-rich rewilding plus being an energy hub?
You immediately hit the standard arguments, right? Like
Yeah.
methane from cattle, which, let's just clarify for everyone, is mostly burps, not the other end.
Good point. And then there are the ethical questions around big dairy and meat operations, calf separation, things like that. But this alternative idea kind of sidesteps some of that.
How so? What's the alternative starting point?
Well, the idea is, what if the cows, even the young males, just roam, graze freely in woods and fields, almost like modern bison managing the landscape?
Biological maintenance machines. I like that.
Yeah, but the key thing is, if they're spread out, you can't easily collect all the manure in one place.
Ah, okay. So no central manure pile.
Exactly, which means you need totally different ways to think about generating energy and protein from the system.
Right. So two paths diverge. Let's tackle the first one. The industrial, the technological fix. This takes us back actually to 1981 research from the U.S.
The Meat Animal Research Center. They were looking at converting manure and plant waste into, well, two things: methane gas and high protein feed.
Basically building an artificial cow stomach.
You could call it that. It's a bioreactor. It hinges on anaerobic fermentation, breaking stuff down without oxygen.
Okay, no O2.
And it uses thermophilic bacteria. These are microbes that love heat, like really love it 45 to 55 degrees Celsius.
That's pretty warm, almost hot tub temperature.
It is. And the surprising thing in that old research was how compact the initial test unit was.
Yeah, I saw that. 5.7 cubic meters. That's like, what, a bit over 2 meters across?
Yeah.
Tiny, really.
Tiny, but mighty, apparently. They clocked a rate of 4.7 liters of methane per liter of fermenter volume per day.
Whoa, okay, unpack that metric. 4.7 liters per liter per day.
It just means it was churning out gas way faster than expected, about 4 times the rate of similar systems they knew about back then.
4 times faster. That sounds impressive. What does that translate to in actual gas volume per day?
From that small unit, about 25 cubic meters of methane daily.
Okay, 25 cubic meters. And in energy terms, a cubic meter is roughly 10 kilowatt hours, right?
That's about right. So you're generating 250 kilowatt hours of energy every single day.
That's good. Well, that's real energy. Enough to power, what, 7 or 8 houses if you convert it to electricity?
Or heat 5 or 6 homes directly with the biogas. So you can see the appeal, right? Waste in, reliable energy out. Seems like a win.
It does seem like a strong case for the factory approach. So why aren't these things everywhere on farms? There must be a catch.
Ah, yes. The
Yeah.
catch, and it's a big one, hidden in the energy balance. That impressive efficiency. Almost all the energy generated was needed just to run the system itself, particularly heating the input slurry to keep those thermophilic bacteria happy.
Wait, seriously, how much energy are we talking?
Between 89 and 94% of the total energy produced just for heating, especially if it's cool outside, say, 10 degrees C.
So, hold on. It's making energy mainly to heat itself. It's like it's working mostly for itself, not for the farm or the grid.
Precisely, it's fighting the ambient temperature. You add in stirring, pumping. The net energy gain is pretty small unless the whole thing is absolutely massive and perfectly turned.
Okay, that takes the shine off significantly. But energy wasn't the only goal, right? There was protein, too. This single-cell protein idea.
Yeah.
SCP, bioprotein, gaprin.
Yes, the chemical fix part. You basically take the methane produced and feed it to other microbes in another reactor.
To grow.
Protein.
Yeah, a protein-rich biomass you can then use as animal feed. It's very high-tech.
But it sounds like you're solving a problem needing protein fodder that large-scale industrial farming kind of created in the first place. That's a fair point. And the research itself was pretty blunt about the economics.
How so?
It basically said this whole complex setup, it only might pay off for huge operations, like 1,000, maybe 2,000 cattle.
Okay, massive scale.
And even then, only if the farmer builds and runs the whole chemical plant themselves, ignoring any value from the leftover digested stuff.
So huge scale, huge complexity, maybe marginal profit if you do all the work.
It really pushes you to ask, What's the alternative? If the cows are out rewilding the forest, manure scattered, what does nature offer? How does the ecological system handle energy and protein using the sun's energy captured by the forest?
Okay, let's shift gears the ecological path. The sources talk about low-tech energy from something called stangbug, pole beech. What's that about?
It's a different forestry approach. Instead of waiting, 80 or 100 years for big timber,
The standard approach.
right, you do continuous, lighter harvesting of younger, thinner beech trees, maybe 20 to 60 years old. It's basically thinning, which is actually good for the forest's health.
And you don't need massive logging equipment, I assume.
Exactly. Lighter gear means less cost, less soil damage. Big win ecologically.
And the energy yield from these poles.
The calculations suggest you get enough wood each year, about 4.5 tons per house, to heat 5 average homes nearby, sustainably.
Okay, direct local heating fuel.
Oh.
But you mentioned a byproduct.
Yes, the fliss, the wood chips. From all the smaller branches and tops, the sources call it a free green resource.
Free resource. You could burn it for more heat, I guess.
You could, but even better, you can use it to improve the soil. It's carbon-rich, builds humus, locks carbon away.
Closing the loop. Carbon back into the soil.
And this is the really neat part, that fliss is also the key to the protein problem in this system.
How? You're not feeding wood chips to cows?
No. You use the wood chips as a substrate, like a growing bed for gourmet mushrooms, shiitake, oyster mushrooms.
Growing mushrooms on the wood waste. That's clever. A circular economy angle.
Totally. The waste from energy becomes the input for high-value food.
So the factory needed massive scale for its bioprotein. What kind of protein yield are we talking about from mushrooms in the forest? Is it significant?
It really is. Just passive cultivation in 1 hectare of beech forest could yield up to 250 kilograms of pure mushroom protein every year.
250 kilos pure protein. Let's compare that. How much pure protein is in, say, one bull calf that might be slaughtered?
Much less. Maybe around 50 kilograms of pure protein in a typical calf.
Wow. So the mushrooms alone, grown passively on wood waste, yield 5 times the protein of one calf.
Pretty much. And remember, this is decentralized, low labor. You combine that mushroom protein with the meat from the grazing animals, maybe add some nitrogen-fixing legumes like peas grown on site.
And you've easily covered the protein needs for those 5 households again.
Easily, using natural cycles, solar energy captured by the trees, and zero external heat input for the protein production itself.
Okay, stepping back and comparing these two systems, it really feels the research is showing that the industrial factory, with all its cost and complexity and energy use,
This is basically working incredibly hard and expensively to replicate services that the forest ecosystem provides naturally for free.
let's break that down. The sources highlight 4 key contradictions. First, manure.
Right, manure versus waste. Forest manure, Gednam, is fertilizer. It feeds the system. Barn manure becomes liquid. A falled waste, a pollutant-needing complex treatment.
Second, energy.
Energy source. The forest harvests sunlight via wood. Passive, renewable. The factory converts methane, yes, but loses most of it as heat, just keeping itself going.
Third, protein.
Protein source. The factory makes bioprotein, a high-tech, costly fix for a problem industrial farming amplified. The forest uses wood waste for mushrooms, plus meat, biologically sound, lower cost.
And fourth, the underlying chemistry.
Chemistry, particularly carbon and nitrogen. The SCP factory needs added nitrogen fertilizer to grow the microbes. The forest uses nitrogen naturally released from manure breakdown and soil bacteria. It works with the cycle.
So the industrial approach seems driven by this, this dogma almost, that nature is messy and inefficient and needs to be replaced by controlled, fast industrial processes.
Pure reductionism. Control and speed above all else. Optimized by simplifying.
And the numbers are stark. Avoiding the factory, that SCP plant, saves potentially 200 million DKK in upfront investment.
A huge amount of capital.
So if the ecological way is biologically better, environmentally sounder, and saves a fortune, why does the factory model still have such a pull? Why choose it?
Now we get into the mindset, maybe even the psychology. It's like a capitalist serotonin fix.
Okay, explain that.
Well, investors, large companies, they often look for quick, concentrated returns, something liquid short-term. Buying stock in a hot tech company, for example.
And the factory fits that model. One big controllable asset you can invest in, scale up, trade shares in.
Exactly. It's a single concentrated point for capital. The forest offers something different, a slower, more spread out return. It builds ecological capital, social capital.
Robust, stable long-term,
Yeah.
but not that instant financial hit.
Right. There's no quick dopamine rush of massive concentrated profit. So the deeper, long-term, maybe more altruistic benefits get overlooked because the immediate individual reward pathway isn't triggered in the same way.
That focus on the concentrated industrial solution also opens the door to, well, greenwashing, doesn't it? And geopolitical issues.
Absolutely. That's a key warning in the sources. Systems like bioprotein production are vulnerable. You could potentially feed the protein-making microbes with methane from fossil sources.
But sell the resulting protein as sustainable feed.
Precisely. It could become a way to launder fossil gas, essentially. Buy methane, sell green protein. It masks the input chain.
So the very technology designed to solve a sustainability problem could ironically extend our reliance on fossil fuels, just hidden behind a different product.
It fits the industrial mindset, prioritize the controllable, marketable output, even if the input chain has issues.
Okay, so wrapping this up, we looked at two ways to approach sustainable farming and energy at a place like Skovsgaard. The industrial factory path demands huge investment and energy just to fix problems it creates.
While the ecological path, the forest agriculture model, seems to leverage natural processes, free biological services to give stable energy, protein, and boost biodiversity with far less capital.
The industrial mindset really seems focused on simplifying everything for short-term economic gain, which feels completely at odds with what we now understand about the need for ecological complexity and biodiversity.
Diametrically opposed, really.
Which leaves us, and you, the listener, with a pretty big question to weigh on. As we face these huge, long-term ecological challenges that clearly demand stable, complex solutions, are we still letting that short-term instant gratification thinking, the lure of the quick technological fix, dominate our investments over the slower, more complex, but ultimately more resilient biological systems?